Good afternoon. It's a great pleasure and honor for me to be here and present you with something related to lightning study. With your permission, I will take my jacket off because it's rather warm, and I'm trying to work very hard. So. The name of the lecture is Unveiling the Mystery of Lightning, and the purpose of this lecture is to present our current understanding of lightning processes obtained during the last 20 years. I should mention that the most significant process in understanding of lightning physics was achieved during this last 20 or maybe a little bit longer years in the United States and Europe. And I should start talking a little bit about physics of lightning to make it easy for you to understand what I will be talking later. Lightning channel is, first of all, a plasma. And plasma is the ionized gas, which is composed of a mixture of free electrons, positive ions, and neutral atoms and molecules. What makes it ionized? In case of lightning, it's electrical field which produces electrical discharge, and this electron avalanche is actually what is the result of electrical discharge. So we have ambient electric field and thunderstorm in a gas medium which produce this electron avalanche and ionizes the plasma. The visible result of such avalanche is a spark, and the formation of a spark is called electrical breakdown. Just remember a little bit this term electrical breakdown because we will use it later on in the presentation. The presence of free electrons in plasma makes it possible to have conducting electric current. And current is nothing else but the directional motion of charged particles under the force of electric field. As a result of a collision between electrons and ions, we have a heat in the plasma, and it produces additional thermal ionization, which makes plasma luminous. It was long believed and presented in the literature interpretation of lightning as a spark, which is absolutely not correct, because lightning is not a spark, it's much more than a spark. Lightning is made of leaders. And here let me introduce you this term of leader. The leader is the channel, it's a plasma channel, formed as a result of continuous transition from thousands of cold corona filament into one hot plasma channel under certain potential gradient near the electrode tip. So here we have the electrode. This is interpretation of the process in the high voltage laboratory. We have electrode under hot positive, in this case is a positive plasma, positive leader. And when we increase this voltage, we start getting breakdowns of different types, and finally we have this funnel of corona filaments. Each corona filament is very thin and cold and slightly luminous filament, and they are usually up to a few meters long. Then you increase this voltage and you have increasing number of these filaments, and we are all focused at the tip, as you see. And finally, as a result of this combination of these filaments, each of them carries very small current, but all together we are like in a projection at this tip, produce very high temperature and form the portions of the leader channel. This is the plasma channel which forms at the tip. If we have conditions ahead of this tip which is conducive to the formation of this process, we have elongation of the leader. So this is how leader is formed. By the continuous elongation of a plasma channel, the leader becomes a self-propagating discharge in ambient electric field prepared by this breakdown process which I just described to you. So this cartoon symbolizes this process. We have, instead of airplane, we have this transition into the leader, and the tail is a formed plasma channel which carries this current. And this is most important process in formation of a leader and in lightning development. What does this process do actually is transforms the energy of ambient electric field in thunderstorms into the lightning current through this breakdown and formation of a leader. Now, what is important also to understand that leader formation depends only on the potential gradient at the tip of the leader. So this cartoon shows this potential gradient is like a step. You know, this is potential value on the tip. This is ambient potential outside. So as long as this potential gradient is above certain threshold, we have this continuous breakdown and formation of a leader and elongation, and it goes on until we have a condition when this potential difference is below a certain value, so very, very negligible, and then this process of formation of a leader stops, and propagation stops, and leader dies, and lightning dies. So this is how it goes physically. So conclusion is that natural lightning is not a spark, but is made of self-propagating leaders of a scale of storm dimensions, which are tens of kilometers long. And basically, there is nothing else in lightning but leaders of two polarities, positive and negative leaders. We are formed slightly differently. Process of flare formation is different, but we are two major components of each and every natural lightning flash. There is exception. It would be in a case when natural flash goes to the ground, and from contact with ground we have a different process called return stroke, and I will talk to you about this a bit later. We still don't know exactly how natural lightning is initiated. There is no way for us to be inside of a storm and see and observe this inside of the cloud. Impossible task. Okay. Also, we know that there is no pointed electrodes in the cloud, and there is no high voltage power point in the cloud. But nevertheless, the physics of leader formation and progression is the same in both high voltage laboratory in nature. So from high voltage laboratory, we know how leader forms. It should be the same process in Mother Nature. But we don't know how it's initiated, its very initial stages. Now, let's talk about types of natural lightning flashes. We call natural lightning flashes are those which are formed inside of thunderstorms. And we are of two major types. Cloud flashes, which are formed inside of thunderstorm and develop inside thunderstorm. Sometimes we see portion of this flash which is extending outside of the storm. And ground flash, which starts and develops in thunderstorm, but then propagates toward the ground and touches the ground. So, in natural lightning, intra-cloud flashes, where of cloud to cloud type. This is example, and you see with this block of luminosity a lot of processes in the cloud which we cannot distinguish in the photograph, and some of these branches are exceeding the dimension and getting visible. And another type, it was called cloud to air discharge, but actually the name of this type of discharges was spider-like. Spider because all these branches reminds me configuration of a spider web, and this type of discharges occur usually in the late stage of storm development when it decays. We propagate under the cloud base, propagate sometimes tens of kilometers, up to 100 kilometers long, and they were sort of mysteriously unknown by nature until recently we discovered that these flashes are nothing else but negative leaders, very similar to negative leaders in cloud-to-ground flashes. We simply have different configuration because we developed during the different stage of the storm. Now, another type of natural flash is a cloud-to-ground lightning. And here I want to, this is a very famous picture for cloud-to-ground flash from National Geographic. And here we see downward negative leaders. This is negative cloud-to-ground flash. We have downward negative leaders, and you see the direction of the branching toward the ground is indicative of propagation, direction of propagation of these leaders. And when one of these leaders touches the ground, you have return stroke. But first, I wanted to bring your attention to these small luminous, also leaders, but of opposite polarity, positive leaders, which starts from some tall structures on the ground in response to downward propagation of negative leaders, which produce very strong electric field on the ground, and from these tall points you have upward positive leader moving toward them. And return stroke, it's called return stroke because the current starts from the ground and goes through the leader channel which touched the ground before, returning to the origin of the flash, which was in the cloud. And this current going from the ground brings positive charge upward to the cloud. So, cloud-to-ground flashes are of two types, depending by their names on the polarity of leader. So negative cloud-to-ground flashes have downward leaders, negative polarity, but return strokes bring in positive charge upward. In positive cloud-to-ground flashes, we have down leaders of positive polarity, but return strokes are negative and carry negative charges upward. So what is the return stroke process? Actually, return stroke is sort of the arc discharge that carries short circuit current between two electrodes. You know, if you have one battery, another battery, or a car battery, you put them together, you have a short circuit, and you will have this arc discharge. This is a big arc, and we have two electrodes. One electrode is actually extended electrode of a leader which goes to the ground, and this electrode has a voltage up to hundreds of millions of volts. And another electrode is some structure on the ground, which is underground potential, which is 0 volt. So when you have 100 milliwatt electrode touching the one which is of 0 volt, you have this arc. And this is the arc of return stroke, and return stroke goes upward. And very similar phenomenon is observed in high voltage laboratory, but in this case you have high voltage on one electrode, pointed electrode from which leader starts, and opposite polarity would be on the plate with 0 potential. Here I finished with description of some major and important elements of lightning. But now we want to talk about physical concept of lightning development. And I should mention that until recently we didn't have a very clear idea about how the lightning flash develops. And what helps a lot and made significant progress in our understanding was study of lightning aircraft interaction. And here is a picture of a result of lightning strike to US Air Force F-111 plane, and it was simply a miracle how pilots managed to land this plane. I don't know how. This was radome, and this is totally shredded by lightning, as you see it. So it's a perfect illustration of the effect of lightning strike on aircraft. In 1980s, NASA decided to start a program addressing very important issue of safety of aircraft, because contemporary aircraft are using not only metal but also a lot of parts made of composite materials. So if your aircraft is not fully metallic body, it's susceptible for destruction of lightning of the type which I showed you before, where you can shred composite material by direct lightning attachment. And besides, modern electronics, which were used in navigational and control system of aircraft, are very susceptible to transits of lightning. So you need to know how to protect it. This was main objective of this program. For this purpose, NASA dedicated this F-106 research airplane, which was old Interceptor, two-seater with a pilot and board engineer, Delta jet plane. And this aircraft was specially hardened to sustain lightning strikes. It was provisions for safety of a fuel tank, special type of fuel, less susceptible to inflammation, special protection for instrumental bay with instruments on this, and it was regularly tested. And this program has two crazy pilots who loved to fly airplane in thunderstorm and being struck. And the funniest thing, we were betting each other who will get more strikes, and the betting was for the case of beer. And we enjoyed this program. I was honored to participate in this program most of the time, and my role was to direct this aircraft to thunderstorm using long-wave radar which detect lightning. And byproduct of this program was solving the mystery of lightning strikes to aircraft. Because until this time, it was sort of discussion, what is the nature of lightning aircraft interaction? It was opinion that lightning actually intercepts aircraft, so that occurs naturally and the aircraft hits the lightning. It was also opinion that aircraft may trigger lightning, but it was no conclusive evidence of one way or another. This program answers this question conclusively. Aircraft F-106B was struck 714 times. Plenty of data. Actually, after a couple of years, NASA said, enough, we have enough cases. But this aircraft was flying at different altitude, first at very high altitude and at low altitude, so it was exploring all possibility of lightning aircraft interaction. Okay, I'm sorry, this was a little bit screwed up. Yes. And the result, this is the result of, no, it's not German. And this is the result of using PowerPoint designed for Macintosh and running it on Windows. So somehow when you put one to another, it starts making this adjustment. So I will read you English as I can. So technical objectives of this program was determining parameters of lightning strikes to aircraft in order to design protection of aircraft and testing criteria. Scientific objectives of this program was determining probability of lightning strikes to aircraft under different conditions and understanding of physics of lightning aircraft interaction. I need to mention to you that NASA was actually interested mostly in technical aspects of this. And it was a long argument, and I was arguing with them all these years until we accepted this idea that without understanding of science, how aircraft interacts with lightning, we cannot proceed this technical aspect. So finally, we came in agreement with agreement, and everyone was happy. So what opportunity we got with this program was that research aircrafts present us with unique ability to measure parameter of lightning as lightning develops with sensors which are practically attached to the lightning channel, which is absolutely unique, not available anywhere else. In addition, this aircraft has a multitude of video cameras, but keep in mind it was 80s, so it was conventional speed video cameras. These video cameras presented us with a chance to observe lightning channel development at a very close range. What we got from analysis of different records on the sensor of aircraft and also radar echoes of aircraft during the strike, it showed us the absolute majority of 714 lightning strikes to NASA F-106 were triggered by aircraft itself. I need to comment a little bit about these radar echoes. What we did, we needed to have aircraft to be followed by radar all the time. So we needed to see aircraft in a beam of radar, and at the same time we need to see lightning in the same beam. This was achieved by using long-wave UHF radar available at NASA facilities, and I was using this radar, and we had clear understanding where lightning occurs and where aircraft is and what happens to aircraft during the strike. And so we had very clear verification that we have lightning strikes to aircraft, which we saw it in radar. We saw all these records, and we analyzed it all together. So how does aircraft trigger lightning? This is a very essential question, which actually helped us to understand development of natural lightning process. When you have this mountain of data and you try to make sense of this, you need to use hypotheses. And if hypotheses fit, then everything fits together. If hypothesis doesn't fit in one place and fits another way, we need to throw this hypothesis away. So, in the search of interpretation, we looked for hypotheses and we found the one for testing airborne measurements, which was hypothesis of lightning initiation proposed in Germany in 1950 by brilliant atmospheric physicist Heinz Casimir. Casimir's hypothesis said that lightning should start as a bidirectional leader from unknown nucleus. He didn't identify. He said it should be some nucleus in a high electric field region of thunderstorm, and it should be bidirectional leader. And the net electric charge on this bidirectional leader, which is the sum of positive and negative charges, should be always zero. So when we deal with aircraft, and this is a fully metallic aircraft, we actually have a form of conductor, perfect conductor, in electric field. And it's electrically floating conductor because it doesn't connect to any power source. So if you have a conductor outside of electric field, it's zero charge. Or if we use some friction with some material, we can charge it, like a triboelectric effect, and it will be uniformly charged. But if we put this uncharged conductor in electric field, it became electrical dipole because it has free electrons. We move in one extremity, and depleted part would be another extremity, so we have electrical dipole. But the net charge is still zero because it didn't connect it to any source of charges. So we found out the hypothesis by Heinz Casimir was proven to be absolutely right for interpretation of lightning aircraft interaction after 30 years of being ignored by the research community. Can you imagine how happy he was when we showed him these results? So he became a very good friend of mine, and I am proud to be called his friend. So let me show you how, in the form of these cartoons, series of cartoons, how lightning initiates on aircraft. So here we have aircraft, which is a conductor with net charge 0, and it's a dipole, because you have on one extremity maximum, distributed positive charges, on another extremity you have negative charges, in electric field shown as E field here. So this is an electrical dipole in aircraft. Now, when you have this maximum electric field and extremity, and it produces this breakdown and start forming a leader. By the way, I should mention that it's much easier to form positive leader because it has much lower threshold for formation than the negative one. So this process starts with a positive leader, and the positive leader is, of course, another conductor. So you elongate this conductor. It would be aircraft plus positive leader. So you have longer conductor. If you have longer conductor, you have the same condition for negative charges, but then you have increasing positive charges, and on opposite extremity you have increasing negative charges. So what happens on this extremity, you have increased charges which reach the condition for breakdown of a negative polarity, which is a higher level than positive, and you have formation of a negative leader. So this picture represents this perfect illustration of bidirectional, because you have one direction, negative going this way, positive going this way, bipolar, positive and negative, and still zero charge, total. Positive leader, aircraft, negative leader, still the same zero charge. You didn't attach power source here, it's all floating conductor. I need to mention that using negative leader starts a few seconds after beginning of a positive one. So there are always two attachment points of the lightning channel of aircraft. But when aircraft, because aircraft is moving, you have an illusion that lightning channel sweeps. I mean, actually it sweeps along the aircraft fuselage, but it's not aircraft, it's not channel moving. Channel remains stationary, it's aircraft moving. So you will see this sweeping action, and I will show you in this. Okay, this is the case already. Lightning is born because you have these both processes. An aircraft is a part of lightning. So can you imagine more advantageous position when you have aircraft as a part of lightning channel, you have all your instruments, you have observation, you can see and measure inside of lightning channel. Nobody had this opportunity before. Absolutely fantastic. So what happens, this aircraft is moving, the channel is sweeping until it sticks to another extremity on the back side of aircraft, and then actually aircraft is pulling the channel. Now I wanted to show you a few video clips of the same lightning strike to aircraft so you can see how it looks like. And on this photograph we show the different location of the cameras. For instance, these red lines show the view angle from the camera behind the pilot, which views the front section of airplane. Then it was a camera in the cockpit looking at board engineer and on the tail section of aircraft, which is lines of white color. Then on the left wing tip, on the upper surface, it was a camera looking forward and seeing most of the frontal part of the fuselage, and it was also a camera looking behind the cockpit, looking upward and seeing lightning channels sweeping aircraft. Okay, here we have a challenge, because when I transfer it into this video, I cannot play, so we need to switch to the video. Okay, I wanted to show you the images of lightning strike different with, okay. So this is a nose view. Okay, you saw first it was bright flash. Okay, this is already lightning which is sweeping above canopy and going toward the back section of airplane. Okay, next one. Okay, this is a camera looking aft view. You see this lightning channel on the right tip wing. Okay, this is a propagated part of the channel from above, and it sticks to the vertical stabilizer here. So this will be the second attachment of a lightning channel. And you see this aircraft is escaping channel, but is still attached to this. And this is lasting for hundreds of milliseconds. Okay, this is a view from left wing. It's all the same flash. Quite an image. Okay, and this is very special. This is a view from the top camera, very close. Okay, you see, this is a lightning channel so close, and this is very unusual. We are within centimeters and meters of lightning channel. And now look at the structure of the channel. It starts remaining as a twisted rope. This is very, very interesting because nobody saw this lightning channel so close. Okay, we can go back to presentation. Okay, just a second. I'm sorry for these interruptions because I couldn't do it any other way, unfortunately. Okay. No. Okay. All right. We couldn't see the development of lightning channel outside because the only cameras we had on the aircraft itself. And convincing visual confirmation of bidirectional leader development came much later from Japan. It was a case of aircraft taking off from Komatsu Air Force Base in Japan in the winter time. And you can see this, okay. And so what happened? It was struck by lightning. I was asked to interpret this video sequence by my Japanese colleagues, and so what happened here is we have perfect illustration of bidirectional leader because upper part of this lightning flash has configuration which is typical for positive leader. Few branches, but very extended, big-sized branches. And the lower part, toward the ground, has attributes of a negative downward leader with this little sort of stepping leaders. But because this is a conventional camera, and each frame is at least 17.5 milliseconds. So it happens so fast that return stroke, which is a very bright channel, is superimposed on these pictures of 2 liters. But this is a perfect illustration of the case of aircraft which initiated lightning strike, which was bidirectional, and then negative leader moved toward the ground, touched the ground, and we have return stroke, and then return stroke hit the aircraft. And after that, we started seeing all the processes of multiple cloud-to-ground flash with several return strokes. Okay. Okay, this is another return stroke, and another return stroke. So this aircraft started lightning and it was exposed to 3 return strokes. So, as a result of this program, we learned about probability of aircraft to be struck by lightning during storm penetration. What was surprising to learn that probability of being struck actually decreases with increasing frequency of lightning and thunderstorms. Big surprise. We had cases when airplane was flying through thunderstorms and pilots were reporting we are going through the firework because it was like 4th of July, constant lightning around us. Boom, 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 everywhere. Aircraft is going through, no hit. And then another situation when you have decaying storm, no natural lightning, goes in, bam, lightning strike. When I talked about this to Air Force, they said it's impossible. I said, this is what it is. So, does it mean it's safe to go through thunderstorm when it's very frequent lightning? At least it's safer. Anyway, it's very interesting result and very important observation for pilots. It tells us that in the decaying stage of the storm, where we still have a lot of electrical energy and high electric field, the sun of thunderstorm, when you bring outside triggering mechanism on board of airplane, it's very dangerous. You will get struck. When you have naturally occurring lightning activity and you have so many natural triggers, adding additional trigger in front of aircraft doesn't make too much difference because this natural mechanism is so frequently produced that it produces and initiates natural lightning. You bring another one as aircraft, outside trigger, it doesn't make too much difference. But it's very, very dangerous to get inside of decaying thunderstorm, you will get hit. Then another interesting result was that the highest probability of lightning strikes occurs at a colder temperature, so you have penetration at high altitude with temperature minus 40 centigrade or lower. You have all lightning strikes initiated by aircraft. You fly lower and probability is less. And also, it's high probability in the area of low precipitation and low turbulence. What was very important for us is to understand the physics of lightning aircraft interaction, which I already explained to you previously. So, when we apply what we learned from lightning aircraft interaction to the physics of lightning development inside of cloud, we still don't know what happened in this nucleus. Okay, what is the nucleus? What are these microprocesses which initiate lightning? It's still mystery, and it's a very difficult task to find out. But we know that we have electric field, and we know that we have from this nucleus bidirectional leader, positive and negative, and all net neutral. And you have this dipole distribution, and you have development of this as bidirectional leader with different distribution in this case. And when you have changing distribution of charges, you have a current which flows in leader, and this is a current flowing in lightning. So as a result of our studies of lightning aircraft interaction, we confirmed the process of lightning development in nature, in thunderstorm, as a bidirectional, bipolar, zero net charge leader. However, after initiation, we have many more additional processes in lightning development, which required special efforts and special tools. And for this reason, one of these very effective tools was used, and it's high-speed video observation. For instance, in this photograph, which is the background of this slide, you see some visual channels of leaders going to the ground and some of them extending, and you feel this huge blob. And we don't know what is going on there, but it's a lot of things, a lot of processes are going on inside. Some of them are so fast we cannot differentiate them, we cannot see it. Some of them are obscured by cloud, so we cannot even see it with visual images. And it was some other techniques developed to analyze processes inside, which are important for understanding of lightning development. But I'm not going to talk about all of them, only to emphasize high-speed video observations which started being used in the beginning of the 90s and especially effective recently. Okay. All right. Here I need again to go to video image. Okay, the first one. Okay, here is the process we start in the cloud, and this is 8,000 frames per second images. You see, there are some slowly moving leaders, you see the slowly moving leaders, and there are these very fast spikes superimposed. Okay, this is something which occurs in the later stage of lightning development, and if you notice, these spikes are getting farther and farther from the region where it's all started. Okay, this is, you see, is moving slowly leading. Okay, finally touching the ground, and after that, we see what continues to be spikes. Okay, let's go back to the presentation, please. Okay, this is integrated image of what you saw before as a video clip. So if we freeze each sequential video picture and put it all together in one frame, we see this structure. And this structure shows us this was the region where all started. And all these bright spikes, you know, like a dendritic structure, but we actually, each of them was moving toward the origin, and in sequence we started farther and farther away from the origin, but still moving toward this origin. It's very interesting, very spectacular picture. And if you use conventional video camera, you will not see this structure. You will see this simply bright blob of light. This was possible only when you have high-speed video system. I need to explain to you in this simplified cartoon what actually happened here. This was intra-cloud flash in the very beginning before it developed toward the ground. So it started as bidirectional leader, this negative leader going into the positively charged portion of the cloud on one side and positive leader on another side. And it's like bidirectional lightning trees. We have like two trees, one made of positive leaders above, and one part of the tree made of negative leaders below. Negative leaders are usually much more branched and highly dendritic, and positive has less and bigger branches. And when negative leaders finally reach the stage when they cannot propagate anymore, and I explained to you this is a condition for propagation. This branch, this part of the double tree, this negative part actually stops propagating and dies. So it disappears. No more lightning there because there is no way to propagate it. But positive tree still has conditions for propagation. So we have, in this case, instead of this bi-tree, dual tree, we have only one part. And as I mentioned before, if you have conditions for propagation of lightning at the top, it still goes, it doesn't care what happens on the tail. So for a while we still have this upward part of the tree propagating, and then a little bit later we start seeing this bright streaks, which I showed you in the video, which are coming toward the origin. Origin was here, between these two trees. And we are starting coming from the origin, and we call recoil leaders. We are still leaders. These plasma channels are leaders, but we are negative polarity. So the nature of this process restores to the bidirectional type. So we have positive and negative leaders, but these recoil leaders are actually going through the traces made by positive leaders before them. So, you know, it's not like breaking fresh air. We are going through the path which was already made by previously developed positive leaders. So we are fast and bright, but we go back to the origin. Okay. Now I need to switch gear and talk about what we are doing nowadays. And we are going from natural lightning to the structure-oriented light, originated lightning. And this is the case when lightning strikes start from the ground structure, from man-made structure. And in this case, initiation of lightning is strongly affected by structure itself, mainly its height. If you have some place with some average lightning activity there, without any tall structure like tower, and then we put tower there, then we will have big difference because presence of the tower will change interaction with tower and with thunderstorm, and we will have many more lightning strikes affecting the tower, which actually starts from the tower itself. So we need to differentiate this type from natural lightning started in thunderstorm. Then there is also a very important fact that if you have this very tall structure on the ground and lightning will be starting from the structure, it's called upward lightning. The probability of this upward lightning starting from the structure is 100 times higher than probability of the structure to be struck by natural cloud-to-ground flash, which comes from thundercloud. So this is the effect of this tall structure. This is very important because if you have it so susceptible to upward lightning, you need to do something about protecting this structure. And Federal Aviation Administration in the United States started being concerned and interested in this upward lightning from tall structures because we start building air traffic control towers in major airports in the United States, in the area affected by thunderstorms, like Orlando, Atlanta, Denver, Dallas, and these towers are 130, 140 meters tall. And of course you have this tower on the background of a flat airport. It's like needle sticking up. So this is good invitation for upward lightning in case of thunderstorm. And just recently, Atlanta Airport has two accidents related to lightning strikes to the air traffic control tower. In one case it was 4 hours, malfunctioning, affecting aircraft traffic. Another case, 2 hours. So it's a serious business. And keep in mind that you have air traffic controllers sitting on very, very top of this tower. So it's quite an unpleasant situation. Except we need to be protected, of course. So this issue became of interest to air traffic controllers and Federal Aviation Administration, and we are addressing this issue by studying lightning interaction with substitutes of these towers, which, FAA didn't want you to put your equipment at airport, and we say, okay, for God's sake, don't do it if you interact with our tower, we're very spooky. So we're not ready to let us to do measurements on airport. So we need to find a substitute for these air traffic control towers. What could be better substitute than TV tower or radio transmission tower? So this is what we are trying to do. I need to mention here that the United States, in this case, is a little bit behind of studies which started and developed in Europe. And it was the radio transmission tower, it is the radio transmission tower in Peisenberg in Bavaria, where we did some measurements, but we stopped doing this several years ago. And there is a facility in Austria, and Dr. Gerhard Dindorfer is in charge of this measurement in Austria, and we do study of upward lighting from power transmission line, which are also very, very tall. And so we did good start in these observations, but we were addressing to some technical aspects. We are interested in both technical aspects of lighting interaction with cold tower, also in physical picture and understanding of the physical processes as well. So right now, what we are trying to do, we did it in Kansas City last couple of years, and for this year and next couple of years, we found absolutely unique place. I was looking for towers everywhere in the world. We found that Peisenberg was not available. We found tower in Brazil, which we are working with. And this place in Rapid City, South Dakota. We have 7 TV towers in a row of 10-kilometer length. And each of these towers is more than 150 meters tall, some 190 meters. Can you imagine? It's fantastic. And you don't need so many sensors. With one video camera, you can have 4, 5 towers in view. It's incredible. It's absolute paradise for research. So this is a view in Rapid City. It's open sky country. It's all hills. There is no skyscrapers. There is no urban environment. It's all unobscured. You can see very clearly. And we put multiple sensors around this, and we can work with this. Okay, so what happens when you have this tower type? This would be the tower, and in this case, in electric field from thunderstorm, you have charges on the tower, which are maximum at the top and 0 at the ground. And when you start moving leader, the distribution changes, so we have current going, and in this case, what we have as a result, we have different picture of lighting development than that in nature in thunderstorm. Instead of bidirectional, we have unidirectional, because it goes from ground upward. Instead of bipolar, you have unipolar, which is positive or negative, but unipolar. And instead of zero net charge, it would be charged. So it's a different picture, but this is not natural lighting. This is the lighting from the ground object. Okay, here I need also to show you examples of these video observations in Rapid City. Remember the streaks I showed you before? Exactly the same streaks in this case, in the case of upward lighting. And we are moving also toward the origin, which is the tower itself. So this is the case of highly branched upward leader of positive polarity with a lot of, okay, we can stop it. Okay, let's go to origin. Okay, and this is a composite photograph for the structure which I showed you in video a second ago. So we see all these streaks again were oriented toward the origin of the flash, but in this case the origin is the tip of the tower. If you make the video image with conventional camera, or almost up to 1,000 frames per second, you will see like you show the development upward. But actually it's wrong, because each and every of these streaks started farther and farther away from origin and moves toward origin. So high-speed video observations show you the true nature of these processes rather than from one observed with different speed. So the development of this type of upward leader started like a positive leader from the tower, and then after a while it was the breaking of this process from the tower, and after that we started getting these streaks, which are negative recoil leaders, very much the same as we observed in the case of natural lightning I showed you previously. So this is important discoveries. Now I'm finishing my presentation with few comments about lightning protection. This is a picture I borrowed from some sites with beautiful photographs, and it shows you how not to be near the thunderstorm. It's a loving couple with 4 contact points on the ground, 4 legs. It's equivalent to a cow on the ground. Perfect situation to be killed by lightning together. So this is how you shouldn't do it. So I don't know. This guy took a high risk to do this photograph, and these guys were very, very brave. Much better and safer is to stand on one leg, because you don't have 2 legs through which you will have a current flowing. You will be underground potential, and praying also helps. By the way, if you remember, maybe Aborigines in Australia have the pose very similar. You know, like we're very comfortable with it. So I don't know, maybe we learned from nature, because Australia has a lot of lightning activity, that this is a good protection pose. So this is the end of my presentation. Thank you so much for your attention.